Okay, everyone, welcome to the second day of the workshop on analytical foundations of deep learning. Today, we start our invited presentations from some very distinguished colleagues. And today's topics are mainly focused on the principal design and the interoperability of deep networks. We have four talks. The first one will be from Professor Max Welling from University of Amsterdam. The second talk will be from Gita Kutiniok from Ludwig Maximilian University. And also the third one will be Professor Bing Yu from the University of California, Berkeley. The last talk will be given by myself. So without any further ado, I will introduce the first speaker of the day, Professor Max Welling. Professor Max Welling is a research chair in machine learning at the University of Amsterdam, as well as a vice president technology at Qualcomm. He has a second appointment as a fellow at the Canadian Institute for Advanced Research. He has served as associate editor and in chief of IEEE TPAMI, also on the board of Neurips Foundation, and also been the program chair and the general chair for Neurips. He is also a program chair for AISTATS and also ECCV and various other conferences. He's on the founding board member of the ELLIS. Max is a recipient of the ECCV Koenderink Prize in 2010. He directs the Amsterdam Machine Learning Lab and co-directs the Qualcomm-UvA Deep Learning Lab. And also that I think the Bosch-UvA Deep Learning Lab. Thanks, Max, for joining us, and it's all yours.
All right, thank you very much, Yi. Yeah, very happy to be here today and talk. I'm going to talk about some new stuff that we did in the field of deep learning. And so the overview for today will be, so the first two topics will be entirely new for me to talk about. So these are papers which have been recently submitted. And so, you know, since this is the first time I talk about it, it might be less smooth, perhaps, than the symmetry and equivariance topic that I've talked about quite a bit before. But therefore, maybe also it might be the most exciting work because it's so recent. So first talk about basically neural PDEs, which is basically the PDE view of deep learning. Then I'll go to the Schrödinger equation, which is also a PDE, and quantum deep learning. And then I'll talk about some symmetries and equivariance and how you can embed those in your neural networks. And I will finally conclude. Okay, so this the first part is work done together with Mark Finzi, who was interning at Qualcomm, and Roberto Bondesan, who is my collaborator at Qualcomm. And the work is to some degree inspired by, of course, this method called neural ODE, neural ordinary differential equation by Chanatol. And you can sort of think, and that's not new, I think many people have observed this. If you think of an MLP as an ODE, you can think of a CNN as a PDE. And sort of the equation here is the equation for a PDE. So we have a function f of x, where x is in some spatial dimension. Think of a two-dimensional sort of space for, let's say, an image space. And t is, of course, time. So you can think of time as sort of the depth of the neural net. So you go sort of continuously through the depth of your neural network. And then the time evolution into the neural net, into the hidden layers of the neural net is given by some operator d, some spatial operator d acting on that function f. And of course, we have initial boundary conditions, which is the function at the bottom, which is where the data is input to the function, is given by some image g. So d is, as we're going to see, is some operator that is local. So like a convolution is a sort of a local operator on a grid. we're going to think of D as an operator which consists of derivatives, and so it acts locally on an image. But then I'm talking about a continuous limit of an image. And so formally, you can actually write down what the solution of this PDE is. It's basically you raise the operator D, into the exponent, whatever that means, and I'll talk about that later. And then you apply that to the initial function G. And so that's the formal solution to that equation. Now, why did I get interested in this? So first of all, f of x t again is the image or the feature field, t is the depth, and d is the differential operator. Now, why did I get interested in this? Well, it struck me that we are treating an image, even if it's on a regular grid, basically really as defined on the pixel values of that image. But I'd rather interpret it as a sampled continuous signal. So I think of an image as a continuous function that I happen to sample values for on this regular grid. And so to give you an example of where the grid might not be so regular, sometimes people take an image and they compute superpixels, and then they compute some feature values at the center of these superpixels, and then they connect them into a grid. And then you get something that looks a lot less like a regular grid. And you can take this to more extremes. You could think of maybe a far sparser sampling of an image where you do some local measurement, and that's going to be the input of your image. So it doesn't become as clear how you would run a sort of normal convolutional neural network on that, because that sort of requires you to have a regular grid. So then people maybe resort to, well, let's say some graph neural net. But if you do a graph neural net, you sort of forget that there is an underlying geometry in this space. So that's really not the solution. And I'll also talk about that later in this talk. There is a way to resolve this using what we call mesh CNNs, which can run on these sort of more irregular meshes. But it doesn't really solve the problem I want to talk about, that this is really a finite sampling of a underlying continuous field. So how are we going to deal with this? Because we also would need this continuous formulation if we were going to interpret this as like a deep neural net as a PDE.
Max?
So therefore, we set out to basically first say, well, we can turn a finite sampling of an image, you can turn it into a continuous function by using a Gaussian process, right? And so on the right here, there's a Gaussian process. We just think that, these are the observations are the sort of the measurements on the pixel values, right? But to turn that in a continuous function, we can just basically define a distribution over functions where the uncertainty is larger in places where we don't observe things, right? But better, sort of smaller at places where we do observe things at pixel values, right? And then we have our continuous representation of our function, except for the fact that it's a stochastic function, if you want, in that there's also uncertainty around the function. And so we sort of set out to use this principle to define a new kind of neural net, and we sort of hit some interesting surprises on the way. Right, so here is, so you can also think of these points perhaps as a set on which you want to do an analysis. So the first part is you have an input image where you have some sampling of your underlying continuous signal, and then you treat it with a Gaussian process, which means that you now have a mean function, it's continuous, and you have a uncertainty function as well, right? Okay, so that's our input. We've treated the input into a continuous function, and now we're going to define an operator which is consistent with a PDE. Okay, so this is a bit of a dense slide, but let's take it one bullet at a time. So here is a sort of a recap of the PDE formulation that we want to follow. And now we need to choose D, the operator, the spatial operator, which acts on the function f. And we chose basically this function in two ways. We first said, well, we want this to be a translation invariant function or equivariant function, however you want to call it, which basically means that we want the operator to act the same everywhere in the image, which basically means that so if you expand the operator, perhaps as a sort of a Taylor expansion in derivatives, then the coefficients which you multiply with have to be constant functions. Okay, so that's easy. And then the second one is sort of more practical. It's sort of related to the size of your filter if you want. So we cut it off after the second order derivative. So you could potentially have higher order derivatives, which means that that you take into account larger distances in some sense in your image. But here, for practical reasons, we cut it off after the second derivative, and that already gives us some interesting surprises. Okay, so then we need to turn this into an operator which acts over a fine. So this is the infinitesimal operator, right? So we want to solve it, and I've shown you can solve it by basically raising the operator into the exponent. That's sort of formal, and we'll talk about what it means in practice, right? So we're going to have a whole bunch of these operators consisting of different parameters, beta and sigma here. And we're going to have some weight value here, which combines these operators using different weight values for different channels, right? So A and B are now the channels of a neural net. For every channel B that you act on this with, you're going to choose a different weighting value for these operators that you have defined. And basically, this is a very general formulation of how you can act with a differential operator, on a sort of a field of feature maps, where the feature map, the index of the vector is given by this channel index B. So then you have to figure out first, okay, how am I going to actually act? How do I use this operator here? How am I going to act with that operator on a function? And it turns out, this theory is of course well understood. The way that you need to do that is by solving a Green's function. So the Green's function is basically a kernel that you then have to actually convolve with your function f. And so here we're convolving for one time unit. That's sort of the depth of the layer that we're willing to go before we start doing nonlinearities. And it basically boils down to first computing this Green function g, which for this operator is actually known. This is just a Gaussian operator with a shift beta and a covariance sigma. Right, and then we basically, we sum over these k indices, which is the different, offsets and sigmas, and then we take this as our kernel with which we convolve f. Okay, so and the nice thing is that we can, if we choose certain Gaussian processes, we can actually do this convolution exactly, as I will come to later. Okay, so that's what it means to apply this sort of this formal solution of the differential equation. It basically means you have to convolve with the Green's function. Now the two terms can actually be interpreted, and it's not super easy to see for some, maybe for others less, if you're less familiar with these kinds of operators. This is sort of a shift. This delta is shifting, is sort of translating, and therefore this beta in some sense is the value at a particular translation, right? So you translate into a direction, and you can sort of think of this as your normal filter value at a particular offset in some direction. And then the second one is acts much more like a diffusion. So this sort of takes a particular signal and sort of blurs it. It convolves it in some sense with a Gaussian distribution. And that's already interesting in my opinion, because this operation is typically not considered in deep learning. You typically have sort of a convolution which maintains a lot of high frequencies, but then this blurring operation sort of destroys high frequencies, and that's already interesting in my opinion. Okay, so then the last step is that you will have to then act with this operator A that we defined here on a Gaussian process, not just on a function, but you need to act on a Gaussian or on a stochastic function. And it turns out that's not so hard. It's again a Gaussian process, but now with a mean, you act with this operator on the mean function, and you also have to act with it on the kernel function, but you have to act on the left and the right argument of the kernel by basically using the sort of conjugate of A, the transpose of A. Okay, so that's sort of well defined. You can do that. So we now have a new Gaussian process, AF, after convolving for one time unit using A. And the nice thing is that if we use the kernel K here of a Gaussian process to be an RBF kernel, which is a Gaussian shape, and we use this particular operator D to define our convolutions, then we have, a Gaussian here, we have a Gaussian here, and we can do this convolution exactly. And so that's kind of nice, so that we can actually, perform this convolution analytically. Okay, so then finally, after we've done that for, let's say, 1 unit of time, we then apply a ReLU nonlinearity, and then we use another mixing matrix M. The reason for this is basically that we want to make things more Gaussian again after the ReLU, so that we can then apply central limit theorem approximations to sort of project it back onto a Gaussian process again, which we can then again convolve with this kernel. So I won't talk about the details of how to do the ReLU and then sort of project it onto a Gaussian process again. There's probably even more sort of elegant solutions in the future for this, but this is sort of the basic setup. Right, so now what we have, we have turned our sampled function into a Gaussian process. We operate with A, which is this kind of new sort of convolution operator, which involves this Green's function. We then apply a nonlinearity. We apply this sort of mixing matrix M, and then we get a new set of feature maps, which have a mean value and which have an uncertainty. And then we sort of rinse and repeat, right? We go layer by layer by layer. And then in the last layer, we do a pooling operation, which is basically we integrate over everything. And then from there, we do a classification as we wish to do. Okay, so we call this probabilistic numeric CNNs because in probabilistic numerics, people use Gaussian processes to solve numerically PDEs and also keep track of the uncertainties. And that's exactly what you can do here too. So the cool thing is that you can solve it this way, and then you can sort of keep track of the uncertainties due to the finite sampling. So if you would, so at the next layer, if you would do much fewer samples here, you'll find that your uncertainties will increase as you go through these layers, right? And you could even sort of choose different points in different layers and sort of optimize where those points need to go. You can sort of backpropagate to the positions of these sample points to place them at optimal positions, and also reason about how many you would need in order to have a certain uncertainty or confidence at the output. Okay, so that's the first part. So then we started thinking, so that's all classical, of course. So then the next thing is that, well, it turns out that Schrödinger equation is also a PDE. And so we started thinking, well, maybe these ideas are also applicable to so the quantum deep learning, which has been of interest to me already for quite a while now. And so I started working with Roberto Bondeson about a year ago on this. And so the first thing you might think is, well, sure, okay, so we have a PDE here, which is, we have some wave function now, also a function of x and t, and there's a time derivative. Then here there is some operator, typically it also has derivatives in it, similar to the one that I showed before. And then there's an initial condition, and you solve it in exactly the same way, right? Putting it in the exponent. And you can basically show that this is a unitary matrix or unitary operator with which you then act on the initial condition, right? And so the typical thing is like these kind of wave patterns that you can create, and basically they are the probability amplitudes that you will find the particle somewhere here in the plane. But that exactly is the problem. So, psi is the wave function. The probability that you'll find a particle at a position x at time t is given by the absolute value squared. But then basically what you've done is you said, well, okay, so really, I sort of believe that if I do an observation, then basically the image is sort of concentrated at one point or something, which doesn't really make a lot of sense. So this is not the right setup to track, to follow. And so we really need something that's more like a quantum field theory. So in a quantum field theory, you have sort of oscillators everywhere. You have sort of quantum things, let's say units, qubits, whatever, at every position in the plane, and they sort of oscillate and interact with each other. So that's what we started out doing. And to give you a little bit, I'm not going to go too deep into all of this because it's, of course, it's very hard to explain, all the details. But I'll just try to give you sort of an overview, a sort of a helicopter view idea of what we've been doing. So the idea is to basically have some kind of grid of qubits, right? And the difference between a bit and a qubit is basically that the state of a qubit is more like living on a sphere, and it's not like either 0 or 1, but it can take on all the values which are sort of on the sphere. So the value of a wave function can take on, even for a single bit, can take on all the values on the sphere. Of course, if you do a measurement, it will have to snap into one of these states. It goes in this state or this state, or it goes in this state or this state or this state or this state, right? So depending on which measurement you do, you basically get either a 0 or a 1 for that measurement. And so, okay, what does a qubit look like? Well, a qubit is basically, a normal bit is a 0 and a 1, but a qubit is basically a complex combination of those two possible values, such that the absolute value of alpha squared and beta squared is 1. So alpha and beta sort of lie on a circle, which is this circle here. The thing is that now if you consider 2 bits, then you have to look at what's called the tensor product of the 2 qubits, which means that now we have 4 possible states. We have 0, 0, 1, 0, 1, 1. Oh, sorry, it was wrong. So this should be 1, 0, and this is then 1, 1. Such that all of these values add up to 1. And now you can see if you go 3 bits, 4 bits, right? So the number of possible states here starts to exponentially increase. And you can get this interesting phenomenon, something what's called entanglement. You can 2 bits in this particular state here, so they're maximally sort of entangled or correlated with each other in the sense that if you would do a measurement 0 for the first qubit, you will always find the outcome 0 for the other qubit as well, even though the 2 qubits could be sort of, galaxies away from each other, right? So they could be light years away from each other, and still, if one would start to measure this bit 0, then the other one would certainly also measure 0, and it feels certainly somewhat mysterious, but that's it's been measured and validated. And so the interesting thing is that these function psi can interfere with each other, so they work very different from probability distributions. Probabilities are always positive, right? In a PDE, you do have sort of this idea that you have multiple paths, and you have to sort of add up all the possibilities, all the paths, all the probabilities along all these paths in order to figure out the probability of a certain event happening. But all these probabilities are positive, and so they add up. But for a sort of a quantum system, you have to add up the complex square roots of probability distributions, and they can be negative, and so they can start to interfere, which means that they can cancel each other out. And that sort of phenomenon happens when you send particles through slits, and where if you would close one slit, then certainly you would have points here, but if you open up both, then those will no longer be there. And so basically the amplitudes coming from here and the amplitudes coming from here, they cancel each other out, which we call sort of destructive interference. Okay, so how do we use that to define a quantum binary neural net? So here we do have our sort of Schrödinger equation, but now it acts on this sort of tensor product of bits, right? So now the input state here is no longer just a function of x, but it's like, in this case, we think of binary inputs, but it is sort of, a specification for the value of every bit in an image, let's say, on a plane. And there's an exponential number of different values that it can take. That's classically true, of course, as well, right? And we do that also for the weights. So we also assign wave functions, superpositions, in this case, for the bits of our weight values, our parameters. So these are also quantum states. And we feed them into unitary operators. So here's a unitary operator is the solution to this Schrödinger equation. And a quantum computer works precisely like that. You have these unitary gates in which you act on sort of quantum qubits. And so we do that here too. So we have sort of these input bits and we act on them with these unitary gates in order to do a particular computation. What we did in this particular work is to say, well, if I wanted to implement a classical neural net, including a convolutional neural net, on a quantum computer, what would I do? So that was the question that we asked ourselves. And it turns out there is this interesting procedure, which we call a quantum phase estimation, which is a unitary operator. And what it does is it adds some additional sort of what you call ancilla bits. So here is a T1 ancilla bits that are being added. So they're all in their 0 state. And they're jointly going to be sort of treated, this unitary operator jointly acts on, these two parameter states, the input state and these ancilla bits. And yeah, so then after that, let's see what happens here. Okay, so we do this for the first layer, or for the first set of parameters. We do this for the second set of parameters. And what comes out basically is a value that is stored here, this particular value here, that is basically is the outcome of a classical operator on input X. So if input X in this case is H, W are the parameters here, you can show that if you apply this quantum phase estimation, in the end, you will do this computation on a quantum computer to get the next value, including the nonlinearity tau, which is a threshold here, the next state of your features. And that goes into yet another quantum phase estimation for the next layer. And then you do a measurement here to read out the final outcome. And then you can actually backpropagate through the system to train this system. I'll talk about a little bit more later. So that was just the implementation of this neural network on a quantum computer. But then we wanted to go one step beyond that, which is to say, okay, let's now also entangle these input states in a non-trivial way that you cannot do in a classical computer. So we had these local entanglers, which would entangle, let's say, the feature values with the parameters. And you would have also these entanglers, which would sort of entangle between these two states. And if you wouldn't apply too many of them, and if the entanglement is only sort of local, then you could still compute things nicely in a classical way. And in fact, we use sort of central limit theorem ideas to actually make this efficient and be able to backpropagate through these kinds of systems. If these entanglers get too large, then unfortunately only a quantum computer can actually compute them. But for these sort of smaller entanglers, you are doing things which are non-classical, yet you can simulate it on a classical computer still. So basically, the outcome of what you're doing is you're basically taking sort of a joint correlated distribution over your features H and your parameters W. So this quantum part here, this entangling part, sort of correlates these things together. And then to compute the probability distribution over the features of the next layer, you basically, so this is a delta function, which is sort of you put H prime equal to FWH, but then you sort of average over this probability distribution that correlates W and H. So that's a more general operation than we would normally consider in a neural net. Of course, you can sort of do this also classically, but the nice thing is if you have like very large entanglers like this, you can compute this very efficiently, exponentially more efficient on a quantum computer than you could do this classically. So we actually did experiments on all of this, and we were, surprised that in this literature on quantum computing, you will not find people who are doing experiments on images that are larger than 4 times 4 pixels, because basically you'll run into this exponential blow up. But the way we set this up using central limit theorem approximations, we could actually do we could look at normal data sets like MNIST or fashion MNIST, which are images of normal size. And we can actually test sort of these systems, which are quantum. We call them quantum deformed because they're sort of still close to the classical system, but not classical anymore. And we could see that we can get modest improvements in this sort of slowly deformed system, quantum system. And the hope is, of course, that if you go to bigger entanglements, then that you can only run on a quantum computer, that these numbers, you know, start to improve. So we can do this for convolutions, no problem. I think I've said most of the things that are here. Yeah, I think, yeah, so we could learn these things and sort of conveniently on the computer, and sort of we could sort of test these ideas even classically of, you know, how they would hold up. Okay, so so then the final part of my talk, I want to talk a little bit about symmetry. So again, sort of inspired by physics and the laws of physics, symmetries are also play an enormously important, you know, role in physics. And of course, this is the theory of general relativity. This is work I've done with these collaborators here, Pim de Haan, Maurice Weiler, and Taco Cohen. And in particular, with Taco Cohen's thesis already, you know, maybe 7 years ago, we started this. Okay, so symmetries play an important role in physics in the following way. People have figured out that many phenomena which looked very different to different observers are actually the same phenomenon if you transform the equations under, you know, the relative motion of the observer. So maybe the most famous one or most well-known one is Maxwell's equations, where one observer would interpret something as an electric field. Yet if you have an observer that flies by that that phenomenon at a sort of constant speed, then an electric field will start to look like a magnetic field for that moving observer. And sort of using Lorentz transformations, Maxwell was able to unify all these equations in one set of equations. And the same thing actually happens for general relativity, where now you can sort of argue that what looks like gravity to one observer is actually indistinguishable to acceleration for another observer, right? And it's just really the fact that you transform an observer, you accelerate an observer, that you could experience something like a force that is very, you know, equivalent to what gravity would give you. And of course, also the standard model of physics is built on symmetries, and the forces of these symmetries are being transmitted by bosons, like the photon and the Higgs boson and the gluon and the Z and W bosons. And you know, there's the symmetry groups U1 to SU2 times SU3, and these sort of leptons here, they're also representations of these groups. Now, what do symmetries look like in deep learning? A little bit more mundane at first sight. So we could basically argue that if you rotate some images around, the prediction you want to make about that image is actually perfectly the same. So, you know, a mole, if you turn it upside down, it should still be the same mole, or maybe even a skin lesion that you wanted to predict. Okay, so that's brought us to this idea of equivariance. And equivariance is basically this idea that if you look at an input image and you translate it, and then actually apply sort of a convolution on it, that should be the same as first convolving and then translating it. And so the closure of this kind of diagram is what we then call convolution, or in equations is basically if you first apply your convolution and then your symmetry transformation, right? Okay, there's this way and then that way. That should be the same as first applying the symmetry transformation and then convolving. Yeah. And so maybe, you know, to your surprise or not, while normal convolutional neural networks are perfectly translation equivariant, they satisfy that particular property, they do not satisfy that property if you rotate them. And I think the easiest way to show is here, which is a movie made by Daniel Worrell, who also had one of the first papers on this topic, like harmonic networks. So if you rotate an image around and you sort of convolve it, you know, you use a CNN, basically you apply CNN. If you apply a normal CNN and then you sort of stabilize this image, which is like you take your camera and you rotate it with the image, then you sort of see this, right? And so you see things are moving around, they're not stable. Or the same phenomenon you see here, if you rotate the 4, as it rotates, it looks like it rotates, but it's also changing, right? But if you use a convolutional neural net that is equivariant, you'll see that at least in good approximation, it will not change if you stabilize the image. So what are the reasons for equivariance? Well, the first thing is that like if you take a normal convolution, you can think of that as equivariant under translations. You save an enormous number of parameters, right? Because instead of having sort of connections from all pixels to all pixels, you now only have these small filters which you apply everywhere in the image. And the same thing happens for rotations. If you also do equivariance under rotations, now you do not have to learn sort of filters which rotate separately, but you sort of manually instantiate in some sense these rotated filters, and therefore you can sort of save parameters in that particular way. So it's more data efficient in this way, and that's very important. It's important that patterns are easier to detect at the next level. So if you think about if I do a translation on an image and it would completely garble up and permute all the signal, you know, after the convolution or after the transformation, then the next layer has a very hard time seeing patterns in, you know, in what the outcome of that operation. Where if things are equivariant, then basically the same operator which you used here at the next layer to maybe, you know, detect a nose could be used here, and then could also again be used at another position of the image. So it's also much easier for the next layer to detect patterns. And the last thing is that abstractions preserve symmetry. So so here's an abstraction of a face. So we have two faces, so they map, let's say, to the same abstraction. Now, if I would, you know, move over the space of all possible faces in pixel space, and I rotate them, and then I would do the abstraction, then I would indeed get a rotated abstract face, and that sort of preservation of structure under abstraction is very powerful, turns out. So how do you then do a group convolution? So the simplest form is this one. So if this is a normal convolution here on this side, so a group convolution for rotations over angles pi over 2 would be like this. So you take a particular filter and then you rotate it by sort of 90 degrees, and then you do another convolution and you store the result in another feature map. So here we have one feature map, but here we have 4 feature maps, one for each orientation of this particular filter. And now you can see, you know, how this equivariance plays out. So if we take our input image like this, and we have these filters, right? We have the filters here in these corners, which are the 4 rotations, and there are 2 types of filters, an eye and a mouth detector. So clearly, you know, if these are aligned with the image, then here you would get 2 detections here, and you would get a detection here for the mouth detector. But now let's say I rotate the input, right? Which is what's happening here. I rotate the input. Now, of course, the detectors which will fire will be the ones which are the rotated detectors, but you also see that the actual detections themselves rotate, right? So here the detections are horizontal and here the detections are vertical. So the operator in this space for rotation has 2 parts. The first part is it will rotate in the image plane. The second thing is it will cyclically permute through this set of feature maps. But so this operator is a little bit more complicated than just rotating, like we had it for translation, yet we can define this sort of operator in the space. And so yes, this thing is actually an equivariant convolution. Now the next step that we took was to say, well, so that's all on a sort of flat manifold, but what if the sort of the image, or you know, the signal lives on a curved manifold? And so here, this picture is actually from a Quanta magazine piece that was written on our work. I recommend it. It's very nice written, I think. And so the idea was here, well, maybe in the future we will have depth sensors and we have, you know, ways to actually have a 3D representation, you know, of the world rather than just a 2D representation. And so also in graphics, there's many applications that we can anticipate where you really want to do deep learning on curved manifolds. And maybe if you talk to an earth scientist or a climate scientist, you know, they have to deal with the sphere, the earth, and if you can do deep learning on the sphere, that would already be quite nice, of course, as one of the simplest manifolds. The problem, though, that you face when you try to do deep learning on a curved manifold is this problem that the convolution sort of becomes, or a parallel transport of your kernel becomes path dependent. Now, on a flat surface, this is not true. You know, you have your kernel and you move it along this path or this path, and it's just the same thing. But if you're on a curved space, you know, if you parallel transport along this path or this path, basically you incur a rotation. And if you unfold this, you can see what happens. So along this path, you can sort of do parallel transport. But if you go through this path, then this and this here are actually identified. And if you identify it, you go in here, but then you rotate and then you go there, and then you sort of get the rotated copy here. So that's the thing that you have to worry about. Of course, mathematicians and physicists have already studied this. In general relativity, this is precisely what happens. In gauge field theory, this is precisely what happens. And basically it's solved by saying that, well, you know, I can actually not really meaningfully sort of, how do I say, apply or identify a orientation of the basis. I cannot do this uniquely, right? So if I have these kind of, if I think of basically a basis of vectors at every point, which you can think of the tangent space of this manifold, and I go through these two sort of curves, they, you know, they rotate, and basically you have to say that there is an inherent ambiguity about the orientation of your basis vectors. And basically what you have to do is you have to sort of mod out or remove this kind of non-uniqueness. This cannot be physical if you want, right? So this orientation, everything you do has to be independent of the choice of orientation of your basis. So people really know how to do this. Yeah, basically you have to, it's very similar to what I just showed before. You basically have many orientations and you just understand that if you go from one place to the other place, how do you transform, you know, these orientations into each other? So you think locally in some sense, and if you move into a new patch, you sort of understand how to transform, you know, this basis into the next basis. But in, you know, to actually understand that and to sort of explain that best, I want to go back to the first thing I said, which is like, okay, one way to deal with points on a plane, or in this case, points sort of on a manifold, is to treat them as a mesh, and then see if we can do sort of a mesh convolution. So I guess, you know, we still have to do the Gaussian process part of this, but you can sort of already see that if you do this with a graph convolution, which is what many people have done, that will actually be suboptimal for the simple reason that you do not take the geometry into account. Right, so we have to do something smarter that is, you know, of this kind, but then defined on a mesh, and a mesh, of course, looks like a graph. Okay, so we set out to do that, and we wanted to come up with equations which look a lot like a graph convolution, but they're not the same. And to see how they're not the same is to basically see that you really want the geometry to play a role. So in other words, we want these two convolutions to really be different, because, you know, for a graph, this is exactly the same graph, but for a geometric object, you know, this angle is bigger than this angle, and so really I want the, you know, the outcome of a convolution where these neighbors will send information to the central node to be different for this geometry than for this geometry. And so the question is, how do we do that and stay close to a graph neural net? So this is basically the explanation of equivariance on a mesh, basically this kind of gauge equivariance that we sort of defined in the continuous space before. Now we're looking at that basically on a mesh and a discretized mesh, where things are slightly easier to explain, I think, although still challenging. So here is your sort of your object. You have meshed up, so there's these points which are on the vertices, and then there's these flat surfaces in the middle. We'll define our signal on these points, these vertices. And in this case, we'll first look at a sort of a scalar signal, not a vector signal, but a scalar signal. And so if we want to do a convolution, we first have to pick basically the zero angle, sort of the x-axis, sort of the zero, where theta, the angle is 0. And I can do this arbitrarily because I already know that the angle, this angle, this choice of basis cannot, be material, cannot have any impact on my final outcome. So I can just choose it arbitrarily, which basically in this case I'm choosing, the green dot to be the x-axis to the right. But in another gauge I could choose the red dot to be that x-axis. Okay, so then I do some kind of gauge convolution here, and I'll get some answer. I will do my convolution here, I'll get some other answer. And these two things now need to be the same. Because if you look at the geometric picture, it's basically the same thing. This isn't different from, both correspond to this thing, which is sort of the geometric picture. But it's only because I was forced to choose coordinates, and I had to put things in my computer to actually compute things, that my outcome could be different, but I just have to force these two answers to be the same. Now for scalar, that's fine, that works out fine. For vector, slightly more difficult, because now the vector in this gauge points in this direction, and the vector in this gauge points into this direction. So really, I mean, okay, so here it means that the convolution has to be isotropic. So it basically means that each one will have to use the same matrix to send this message from here to here. And that would actually be similar or identical to a graph neural net. For a vector feature, it's actually different. And in order to force that these two results will actually correspond to the same computation, you now have a constraint on your kernel that looks like this, where G is the sort of operator that acts on, on this kernel that acts in this space. And these are two matrices, which are called representations of the group that we're considering, which in this case are rotation matrices. So now we have to solve this equation, so which puts a constraint on the kernel. And with that constraint on the kernel, I can certify that this result and this result are the same. And basically, I'm saying that I can make sure that I can transform this result into this result by an appropriate transformation. Okay, so the whole thing will look as follows. Let's sort of focus on this part here. In order to do a convolution, I have to take a feature vector at the neighboring point, and have to do this for all neighboring points. I then have to first align the gauges, which is exactly what I did here. So I have to sort of align the gauge of the point where I'm going to and the gauge of the point I'm coming from. I have to align those two. So that's basically making sure that I align those gauges. Then I also have to parallelly transport, so over this edge. So in this case, that's quite easy because it's just a straight line, right? So I start with, a frame which is sort of oriented this way, and then have to reorient it so that it's aligned with this frame here. And then I have to align the gauges, the choices of the bases, and then I just move this vector here, and then I can just do my convolution. Okay, that part might have been a little abstract, but in the end, what happens is that the convolution on this mesh looks very similar to a convolution on a graph, which is written out here. It's a self interaction, and then it's sort of a kernel which looks at all the neighbors. But for a graph convolution, this has to be isotropic. The kernels will have to be the same for all the neighbors. Where for this mesh convolution, what comes out in the end is that this now no longer is isotropic, and the kernel can depend on a angle. And it can do so in the right way, which is it transforms correctly under these sort of gauge transformations. Okay, then to conclude, so I've talked about PDEs, and I find that PDEs are the more fundamental description of deep learning. But of course, to do that, you have to go to the continual limit. And I think the appropriate way to do that is to use GPs to describe the signal or to interpolate for the signal. It's very natural, and then you have to run your PDE on these GPs, which you can actually quite nicely do. It also segues nicely into quantum neural nets because the Schrödinger equation is a PDE after all. It's just a bit different because you now have to work in a different space, which is the tensor product space. We've looked at qubits. For now, we're also looking at more elaborate signals, continuous signals. And you find that in a quantum computer, you can sort of leverage these phenomena which you do not have in classical neural networks, like entanglement and destructive interference. Now, symmetries also play a very crucial role, so we have to still integrate them, but we are working on that with the GPE, with the PDE picture. It's quite natural actually, because you just want now your Hamiltonian to commute with your symmetry operators. So we've worked on these symmetries in the context of neural nets, and we found that on curved spaces you have to do sort of gauge symmetries, and on global and on sort of normal flat spaces you use sort of global symmetries. Yeah, so basically what's happening is that we're importing a lot of interesting ideas from physics and mathematics, and they guide us to sort of think differently about neural networks. And I think a lot of really interesting foundational stuff about deep learning can still come from that. And with that, I want to conclude.
Thanks, Max. So probably we can, we have a few more minutes to take some questions from the audience, if any. So actually, I'm not able to see anyone's.
Can you hear me, Max?
Yep.
Hi. I had a question about the first part of your presentation, particularly when you had that architecture slide that was transforming images into a Gaussian process and then applying the differential operators in multiple layers. Yeah, here, for example. So this looks very much akin to simply mapping the input images into a Hilbert space and then applying linear operators in the Hilbert space, followed by some sort of nonlinearity. And so I'm curious as to whether the Gaussian process part is essential, or whether we could simply think of these as signals in a Hilbert space.
Yeah, so I think that's related. So it's, of course, it's a different Hilbert space than for the quantum theory, but I think you can, the Gaussian process formulation is certainly connected to a Hilbert space, right? So you can think of a Gaussian process basically as a kernel method, and we know that that a kernel method, okay, something popped up on my screen. Yeah, and we know that a kernel method can be described in this RKHS Hilbert space, and this is very similar here, of course. I do believe that the Gaussian process part is important, and the reason is that if you think about basically a bunch of points, I mean, if you would have an infinitely dense network, if you would have access to the signal, the continuous signal, I think your comment would be right? So you can think of the PDE basically as solving things in the Hilbert space. However, if you just have a finite sampling and perhaps a sparse sampling, you would first have to sort of map onto a continuous function. I think the most natural thing there is to use a GP, but it does actually correspond to a Hilbert space, but it now is basically a stochastic function of yeah. So I think this theory is certainly very relevant, I would say.
The other question I had over this part is, what about learning? And how are the filters learn and what changes?
Yeah, so it's, you can just backpropagate through this whole thing. So these are all, these operations that we define, they're all perfectly, backpropagatable. So you can just define the function layer by layer and, apply autodiff on this whole thing. You can train basically the parameters of this network, and the parameters of this network are basically these betas here, and these sigmas here, and these W's here, and then we have actually these M's here. So all of these things can be trained fine. So yeah.
Great, thank you.
So is there any other questions from the other audience? We probably can take one more. And also we have a break between after the next talk. You know, if the speaker or some of the audience want to hang out, have some extra question, we have extra time then. The rest, you know, of course, can take a break, but if you have question, you can chat to the speakers.
Yeah, the only problem is that it's kind of late here, so I'm actually
Yeah,
going
probably
to have
not.
dinner
Maybe
in a minute.
Gita.
But
Yeah, maybe Gita. Yeah. All right. So
I have one more question if there is time.
Sure.
Regarding the third part, I guess the definitions and the framework are applicable to equivariance of 2D data with 2D transformations and 3D data with 3D transformations.
Yeah.
But in many applications in computer vision, I might want to say rotate and translate an object in 3D, but what I observed are images. How does the theory extend to those situations?
yeah, so that's interesting. So in that case, I think you need to do something quite similar to the Gaussian process, right? So what you need to do is to first map the signal that you do not observe into a latent structure. So you basically have to say, I'm first going to reconstruct the signal in 3D, but with uncertainty attached to it. So a probability distributions of possible signals that correspond to the observation that I'm currently seeing. So you can probably do that with some kind of encoder structure. Maybe a VAE can be used to train such a system, right? So now you have a probabilistic description that could be continuous, right? Or not, whatever. But then you have this probabilistic, and then you apply your symmetry transformations in this 3D space, right? So the symmetry applies in this sort of latent 3D space, which includes uncertainty now. And of course, the decoder would then correspond to, maybe rotate and then project back again, including the uncertainty. So you would sort of get a distribution over possible images that you could see if you would rotate an input image, right? So you take an input image, you infer the 3D image, you rotate, you then project back, and then you should get a distribution over possible things you could again see in that two-dimensional image that would correspond to the rotation of the input image.
Okay. Yeah.
So now I have another question. I noticed that there is a beautiful mapping between the formalism that you used from physics and the formalism we have for the neural net, CNNs. So should we be satisfied with that, with being, with the mapping at the formalism level, or can you also go somewhat deeper and say, okay, phenomenologically or process-wise, there is some correspondence that we can identify?
So I'm very fascinated by this question, but I don't 100% understand it. So you're saying, what is the relationship that you allude to between the formalism?
Not the variables that we have, but what they represent. It's a little bit more kind of a process level rather than representation level. Can we see some correspondence between the world that your formalism, for example, quantum physical formalism is capturing versus the computation that is being captured by the CNNs?
Yeah, I don't know. Yes, so I don't know. That's a fascinating question, but I really can't quite answer that, I think. So to me, to me, a neural network clearly what it does is it abstracts, right? So it takes an input and it sort of abstracts it into increasingly abstract representations of the world. And the more abstract you become, the more meaningful to the human mind, basically they become objects, the things that we reason about.
Mm-hmm.
But that's true for a neural net in general. That has nothing to do. Yeah.
So Narendra, that's also the purpose of the workshop, right? I think we were trying to find out both the mathematical and physical meanings of deep learning.
Right.
Friday, we actually specifically have dedicated a brainstorming session, specifically going to have, drawing open questions, discussions on several aspects of learning. So that's actually the purpose for that. Thanks a lot for the great question. And also that I know it's late, and thanks a lot. I think that Max and Gita, the next speaker, are from Europe, and we really appreciate that. That given the time differences, they're able to still give the talk. Thanks, Max, for a great talk, and truly appreciate your help. Okay.
Thank you.